Welcome to the solutions video for the decay equations exercise as part of our nuclear decay lesson. So we're going to go over the 4 decay equations that I asked you to work out as part of the lesson and see if we can get them right. So the first of the questions that I asked you to do was to look at the alpha decay of americium 241 AM, if you can find it in a periodic table, which has an atomic number, as I wrote, of 95. And if you don't believe me, here is my periodic table. Americium is down here, atomic number 95. So we need to do an alpha decay on this. So we remember our initial nucleus is americium 241. And that is then going to decay into 2 products. One of them being an alpha particle, which you'll recall is alpha 42. So 4 for its atomic mass and 2 for its atomic number. And from there, we just need to work out what the nucleus is going to be that is left over. So to do that, 95 take away 2, because we need to conserve the number of protons, is 93. And 241 take away 4 is 237 to conserve the number of protons and neutrons combined. Now we get the periodic table. Let's have a look. What has an atomic number of 93? It's neptunium. I'm going to lift that up a little bit more. Neptunium has an atomic number of 93, and so NP goes here. You will have needed a periodic table to find that symbol, I'm afraid, because I didn't have a full periodic table to put on the screen for you. But your answer, 24195 AM goes to 23793 NP plus 42 alpha. The second one, part B, was beta decay for sulfur 35. So 35 was our atomic mass, because that was the isotope of sulfur that we were working with. And I also gave you the atomic number, which is 16. So let's do it again. 35, 16, S goes to. So we know we have a beta particle, and that has an atomic mass of 0 and a atomic number, air quote, of -1. It doesn't actually have -1 proton. It is an electron. So because of the change in the decay from a neutron to a proton, we have that -1 to keep things conserved. So 16 take away -1 is the same as 16 add 1, makes 17. 35 take 0 is still 35. So we need to look for the atomic number 17. 17 is chlorine. It's a little bit small probably for some of you on mobile, but Cl. And that is the answer to that one. You don't actually hang on, plus. 3517 Cl plus 0 minus 1 beta. Now the third one was a gamma decay, and I gave a few extra hints to try and help you with this one. So part C is gamma emission from platinum 192. Platinum has a symbol of Pt. 192 is the atomic mass, and the atomic number I gave you was 78. So the hint I gave you is about pre-gamma nuclei. So essentially, gamma emission comes from nuclei that need to reconfigure themselves to a more energetically favorable configuration, to use some of the slightly longer speak. And that means that they are what we call excited. So what that means is that you would typically write your initial nucleus like this. So instead of writing it as 19278 PT, you would write it with this little star next to it in order to show, hey, this is an excited platinum 192 nucleus. And it's then going to gamma decay. So there's gamma, which has, you remember, 0, 0. You don't often actually write the 0, 0. You can just write gamma. And that means that these two numbers are not going to change because both of them would be subtracting 0. So you end up with regular platinum 192. That is definitely the trickiest of the equations that I've asked for this section, because it's not always intuitive to think, oh, it's just going to be the same. The only difference is it was excited, and now it's not excited, because it's undergone that gamma emission, meaning that it no longer has this excited extra energy that's been carried off in the gamma ray. So that was your answer. It's the same numbers, same symbol, just remove the star and add a gamma at the end. A little bit more awkward, that one, so if you didn't get that, I completely understand why. It's one I'd normally talk through with a class. And finally, part D, we were doing neutron emission from tantalum 181. So tantalum is atomic number 73, it's down here. Ta, atomic number 73, mass number 181. Nice and simple. So we start off 181, 73 tantalum. That's our initial nucleus. And then that is going to go to, well, we have a neutron, because a neutron is emitted. And neutron is 1, 0, because it's not a proton, but it is a neutron. So no atomic number, no charge, if you like, and 1 atomic mass. And we need to balance the numbers. So 181 minus 1, 180. 73 minus 0, still 73. So we're still on tantalum, but instead of being on tantalum 181, because that's where we were, we're now on tantalum 180. We haven't changed element because the number of protons has not changed. That's a very important thing to remember. We haven't changed proton number, we've only changed the number of neutrons, so the element doesn't change, it's just a new isotope. Right, so those are the solutions to all 4 of those for your americium, sulfur, platinum and tantalum. Now make sure to make any corrections you need to in order to so that you've got the idea in your notes and in your answers. And then when you're ready and you're happy, the link to the main video will be in the description.